Welcome, everyone. Thank you for joining us today. My name is Michelle Branzlowski. I'm the Global Marketing Manager here at Control Station. Our topic today is how do you detect your mechanical issues in your plant? And with me today, I have two top engineers with probably, I'd have to say, over 50 years of experience in process control. We have the Director for Europe, Middle East, and Africa, Damian Monroe, and one of
Hello
our
guys,
expert field sorry, David. And one of
just
our
saying hi,
expert
that's
field
all, apologies.
expert field engineers, Brad Anderson. So with that, I'm going to tell you a little bit about Control Station in case you're unfamiliar with us. So we like to partner with our customers to solve their process control needs by using a combination of world-class software and expert services. We have offices in the United States and Ireland and have successfully deployed our solutions, and we support and we are installed in over 70 countries worldwide, and we're still growing that. We partner with 1 out of 2 manufacturers listed on the Fortune 500 company. All right. So we're going to start with something fun today, something a little interactive. And in a minute, I'm going to pull up a poll, and all you need to do is take your mouse and click on your screen. You should see it in a minute or two there. All right. Operation and maintenance costs for a control valve are influenced by what? Select all that you think apply. Valve selection based on application, quality of valve design and materials, digital information on the valve health, or the current cost of a loaf of bread. So I will give you a few minutes to, well, about a minute or so to participate in that. In the meantime, I'm going to do a plug for our final webinar for 2023. It is December 5th, and it's going to be how are oscillations affecting your process? And we're going to be covering a case study on this one. So look for my email or go onto our website and sign up. All right, we got about 70% of the vote in, 75, and then I'll be sharing the answers. Okay, that looks good. I'm going to close it, and I'll share the results. Okay, thankfully no one picked the cost of a loaf of bread. So 86% think selection based on application, quality of valve design and the materials, and digital information on valve health. All right, I'm going to hide this, and then I would like to hand it over to my colleague, Brad.
Thanks, Michelle. When you think about control valves, you have a picture here in front of you that details the total cost of ownership. You can see from the diagram that engineering, valve price, spare parts typically make up only a quarter of the total cost of ownership of a control valve. The other 74, 75% all has to do with the operation and maintenance of the valve, the day-to-day work, repair costs, items you might have to perform during a plant outage. So you think, you know, with that in mind, you think, that's a pretty wide discrepancy. So do we need to put more effort on our valves into the engineering up front to get what we need out of the control valve? So if we switch to the next slide, Michelle, you can see typical industry analysis that you have valve sizing issues, valve too big, valve too small. Uh, if the valve's too big or too small, you're going to have a process impact. You're going to have a valve that's not in its optimum control range. And when the valve is not in its optimum control range, your control strategy for that loop is going to be compromised. You have the issue, in addition, when the valve is too big, you're going to affect the lifespan and the reliability of the valve. Anytime you have to work on a valve, especially when it comes to major repair or replacement, that's a big deal in a process plant. Having
Brett, I think, Brad, I think that's very interesting with the valve too small, that it has no lifespan or reliability. But really, the key comment over there is you've no control. With a valve that's too small, it's never going to. It's going to be stuck full open for its life. You know, which is as bad. You know, but it has no control on the process over there. Sorry for
yes,
interrupting him.
yeah, essentially in that case, Damien, the valve is not moving. It's just when the loop is in operation, the valve goes to wide open and just sits there.
Yeah,
So
yeah, absolutely.
other issues, far as the mechanics of the valve, you end up with stiction. And my colleague Damien, he'll be addressing stiction in some later slides. But you can see it impacts the process, and it impacts the reliability and the lifespan of the valve. You can see no positioner. That's going to impact the process. And in process plants, unfortunately, we can't, in many cases, have two valves, one for the control aspect and one for tight shutoff. So when you have a control valve that you expect tight shutoff from, you are going to compromise the controllability of the loop, because with this tight shutoff, meaning no leak through, it's going to affect the lifespan reliability, and it's going to impact the process some. And then you run into issues with seat damage. Valves that are working a lot, they're going to wear out the seats in the valve, and other issues that can cause seat damage if the seat is not designed for the process fluid that's going through the valve, whether it's of a corrosive, meaning the seat will be attacked chemically, or it's erosive in nature, whereas the seat will be worn out from the mechanical friction of the fluid passing through it. All those are going to impact your control. Plus, if there wasn't the proper effort applied up front, which I have encountered a lot in my industry career, for the design and installation of the valve, you're going to end up with issues ranging from poor control, plugging, the issues I just mentioned with erosion and corrosion. So I feel from my experience that there has not been in most cases, the proper emphasis placed on upfront design. Damien, what about you in your
Yeah,
experience?
no, absolutely. Yeah, it's it's the seat noise there is something. It's something that I always thought about. Noise on a valve. If you can hear the valve, that means it's working really hard. You know, the material passing through it is going through a very small opening, and if there's any kind of corrosive or erosive components in that, noise means abrasion. Is the reality of it. That seat damage can radically affect your process. You know, anybody, well, I spent some time in the offshore oil industry, and wellheads can be screaming at you, but they are designed to take those velocities and that erosive material. In our process, in normal process production, noise is not good on a valve. If you hear the valves whistling or whining or any kind of noise, it's something that should be investigated. It's not going to cause short-term problems, but certainly will add to long-term reliability, maintainability conditions that would cause. Design is something that we can't really fix. Well, no, you can fix design problems, but it's going to take investment of time, money, and energies to do it, and it's perhaps one of the hardest things to resolve, particularly in installed positions. Back to you,
Thanks.
Brad. Yeah.
Thanks, Damien. Michelle, or Damien, if you could switch to the next slide. So we talk about the consequences of no control. I like to think of the analogy of an automobile, or a car as people call it. The control valve is for whatever control algorithm that you're using in your DCS or PLC. The control valve, well, the final control element, but in most cases it's going to be a control valve, is what puts that action into the process. The same way with your automobile or your car, if you don't have good tires, that the tires is what puts all that horsepower and performance from your automobile to the road and makes it go. So if your valve is not working correctly, you're kind of stuck there, because you can have all the bells and whistles you want in your control system or your control algorithm, all kinds of fancy advanced process control. But if your control valve cannot execute what it's told to do, then all this money and time you've spent developing these advanced control algorithms are all for naught. And the way this no control or lack of control manifests itself is it accelerates the wear and tear on your control valve. And it then, when you have the wear and tear, then that leads to areas where you're undermining your ability to control the process where you want it. If you can control the process where you want it, obviously you might be able to save energy. You can control your feed flows tighter and decrease your raw material usage. You should have less product variability. So all these things are affected when you have poor control. It comes through with a decreased efficiency of the entire unit or system.
Brad, I call that consequences of the no control, the why am I here question. As an automation or a process engineer, you end up standing in front of a PID and a valve and an instrument and going, well, what has brought me here? Because it's not working for the operations, etc. And then you have to try and analyze what are these consequences. What is it not doing for us, and why is it not doing it for us? Is the thing. But it sounds like a deep and meaningful question, but it's the why am I standing in front of this process now? What has gone on before to get me here? And it's those considerations that we want to kind of explore as part of this.
Ultimately, it's affecting your plant's bottom line.
Absolutely.
So if we could jump to the next slide. We'll talk about simple control loops. Next slide. What we have pictured on the slide is a simple control loop. In process plants these days, it probably makes up at least half of the control loops in a modern process plant. And the job is simple. the operator sets a set point, and the control loop works to control that flow at the desired set point. So if we move to the next slide, we have some loop dynamics. We can see we have a direct acting situation where you have a direct acting process. You increase the controller output, and the PV increases accordingly. You decrease the controller output, and the PV decreases accordingly. And then with a reverse acting control loop, when you're in automatic mode, if the flow rate gets higher than set point, then the control output must decrease so that you bring the process variable back to set point. So in this case, the controller action is the reverse of the problem. And flow loops are typically steady state. And what we mean with steady state, it's a self-regulating process. Wherever you set the valve, it seeks a new state and should stay there, barring too many unforeseen circumstances.
Yeah, Brad, the majority of process is steady, is that self-regulating. You know, it's the non-self-regulating systems are those level controllers that if you open the valve, you'll fill the tank to the maximum rather than stabilizing out at pressure, temperature, or flow. And the majority of processes is seeking to find that self-regulating process from that valve change. Is what it does. It's really finding that balance, though. With that is what we want to try and do, is be most efficient with that process. One other thing to note is that the direct acting process or the reverse acting controller can get inverted with the failed state of a process. Is something. So what you may think from a control point of view is to drive the valve. To increase the valve position, you may have to work against a spring in the opposite direction to overcome that fail-safe condition. So just something to keep an eye on that action is the way in which the controller action and the process action is.
Thank you, Damien.
Mm-hmm.
If we can jump to the next slide. So the flow loop, which is the major workhorse in our process plants, it's typically rather quick, works without much delay. In most cases, the proportional integral controller is sufficient to control your flow. And with these fast flow rates, you need your valve to respond accordingly. And if the valve is limited by mechanical issues, which Damien will elaborate on in further slides, you're going to hinder your ability to control flow at set point, which can cause all kinds of problems, which we've already discussed with wasted energy, decrease in process yield, decrease in process quality. So we need, in flow loops, you need a valve that's going to react quickly to the desired output.
And Brad, the one caution I would say to that is that just because you can doesn't mean you should. You know, because you have a fast acting flow process and that it can respond quickly. Do you need to respond that quickly? Is the question I always ask people that are tuning, because if the process can change its direction or its position in 3 to 5 seconds, for example, or even 30 seconds, will your downstream process manage that change? You know, manage that rate of change? So in reality, your flow is going to change to disturbances. But if you overreact to those disturbances, you're just going to push the other bump down the process also. So a respectful change in flow systems will allow your downstream temperatures, etc., to react at their rate of change. It's something that you see regularly is, well, the flow loop reacted in, the time constant was 3 seconds. So that's how I worked to control in that speed. but the downstream system was a 3-minute system, so it's no way can it deal with those changes. It's just something, and one of my, just because you can, does it mean you should, was what I would say to it. Think about where that flow loop is in your process. And that wear and tear, if you're driving that process hard and fast in 2 directions in response to change, downstream systems are going to see those fast load changes and then have to try and deal with them, I suppose, and that can cause further problems.
So I guess the moral of this, Damien, is no loops, control loops, that is, work in a vacuum. They're all part of a system, and you have to be conscious of how a change in one loop affects the whole system.
Very much so, absolutely. Well, that's a good. I'm going to use that. No loop works in a vacuum. It's a very useful, a very succinct statement of it. It's something that we all struggle with. We have back to my why am I here question. I'll stand in front of a loop and say I need to control this in 3 seconds, but you're not considering the downstream or the upstream process that's going to see that load change in that time and the effect that it could have on it.
Okay, if we can advance to the next slide, I will hand it back to Michelle, and she has another poll question for everyone.
Thank you, gentlemen. All right. I'm going to launch this, and you should see it on your screen in a second or two. All right. How do you personally find mechanical issues of control valves at your plant? Select all that apply, hysteresis. You look to the stars in the sky, deadband or stiction. So I will leave this up for about a minute or so. Please participate. This is just kind of fun. Gets everyone involved, tests your knowledge. Okay. No. Brad and Damien, thank you very much for pulling in your personal experience during this webinar. I think that's very valuable and can really hit home to our webinar attendees. All right. Looks like I got the majority of you in. I'm going to close this and I'll share this. Okay. All right. I like the person that says they look to the stars. 58% say hysteresis, 84% say stiction, and 42% say deadband. So with that, I'm going to hand this back over to Damien.
Okay, thanks, Michelle. Interesting results there. And we're going to actually talk through those 3 components there, stiction, deadband, and hysteresis, just to give you a dictionary definition of them, but also then to understand their potential causes, because that's part of my why am I here question. Why is this valve not doing what I wanted to do? What has changed? Have we worked the valve too hard? Is there a quality issue within the valve components? Is there a maintenance issue? All of which can be related to those mechanical issues that have caused our poor performance, or caused you to be standing in front of a process at hopefully some reasonable hour in the day, but potentially can pull you in operationally at different times. So let's have a look at a couple of those 3 components. We'll do stiction first. What is stiction? Well, it's one of those modern makey-uppy words. Stickiness and friction has been combined together. The valve has got stuck due to friction. Now, the friction has been caused by the packing, or the seal on that valve has dried out, has overheated, has been overworked, and is causing the friction between the packing and the valve stem to exceed the break free load that the pneumatics are putting on the actuator. Causes typically are due to excessive use of the valve, excessive stroking of the valve, and lack of maintenance on that process, lack of lubrication, lack of repacking of that system, which can cause it. So, you know, to that point as to, well, what causes excessive use, overuse, over stroking of the valve? And in reality, it's our process that's doing it. Our process, our expectation is perhaps too aggressive or too oscillatory, and it's causing the valve to move too far in one direction and move back and has to keep oscillating. It's over aggressive control. You may argue that we need fast response, but fast response is going to result in overuse of the valve, which will then ultimately lead to wear and tear. If you have an adequate, accurate, and efficient maintenance program, that you repack those valves every year, whether they need it or not, you can avoid that. But again, it's a very costly addition to your process, in that you're changing your valves whether they need it or not, or at least doing maintenance whether they need it or not, rather than doing it on a scheduled or a condition-based system. Again, a lot of companies are moving away from the arbitrarily shut down, do maintenance on everything. They're moving, and have moved over the last years, to do on condition, do performance monitoring to confirm that this process is starting to drift and is something that we can look at. But apart from that, how do we understand Stiction, and how do we understand how much we have and what we need to do with it? Well, to measure Stiction, there's a very simple test that you can do, although it takes a degree of taking control of your process. Basically, you need to set the controller to manual, set the output to manual, and incrementally increase the output in very small increments, or relatively small increments. So we're stepping up the output by, in this example, 0.1%, and we're waiting, 0.1%, and we're waiting, and we're slowly moving up the process there, until at some point, as we move up the output, we see a process change. We see the process step to the new, to accept this addition of flow, heat, pressure, temperature. In this example, it's flow. And we see this step in our output. We can then measure the amount of steps we did, which is approximately 1%. So we have 1% Stiction on that valve. Is the easy way to do it, or in reality it's the only accurate way to do it. One thing to note on the time you wait between each one of these changes needs to be sufficient to overcome the dead time in your process. The dead time is from the time the valve moves to the time the process variable would normally change. Now, in this example, the process variable is not changing because the valve hasn't moved. But this, in a healthy system, this time period here should be the dead time of your process. If you don't know the dead time of your process, a quick walk out to it and look at the distance between the valve and the instrument, and do a rough back of the hand calculation on, it takes about 30 seconds, or it takes 3 seconds for that liquid to reach that instrument, and you'll then know roughly what it is. I would suggest waiting 30 seconds. If you haven't the ability to go out to it, it should be more than sufficient to allow this time to occur. If you don't wait that time, then you won't see the instantaneous the step change. But just as I said, a very quick and simple test. Does require you having to go to manual, and some sites are very reluctant to do that. You could perhaps, set point changes are going to give you some indication on that. And actually, my next slide is something that you could perhaps adapt to see that, to do it on a set point. This is doing a manual change, but you can see the manual output is being stepped up, and we're getting equal size changes on the step up, or relatively proportionate changes, slightly larger here, from a different reason, but we're getting that response. but more importantly, comparing before the final step to after the final step, we see that with the valve position presumed to be in the same 75%, we are getting a difference in the amount of energy's been balanced from here at 140 up to here at 160. So there's a 20 degrees of temperature, for example, or 20% of PV difference in that value. And again, that's another indication of stiction, that when you move up the profile and you move back down the profile, that you don't return to that normal mode of operation. Again, with process control and PID accuracy, repeatability is key. If it's not there, question it. And the likelihood is it's a stiction, that the valve has not come back. If you stepped down again, you're probably going to recover this value here. But it's useful to as two methods of measuring stiction. You could do this with a set point. If you step the set point up a couple of times and then stepped it back down to your normal operating, if it doesn't stabilize, it is going to attempt to recover, but you will see this lack of match between those is what will happen.
Damien, if I could interject there.
Yes, go ahead.
The difference between this slide and the one before it is that when the one before it, that example, there were 0.1% steps in controller output, which is something you would typically see when a control loop rather, is in automatic. That's how you want to check your stiction, is when the loop is performing, for lack of a better term, normally. When you make large changes, like you would doing a controller bump test to determine control loop parameters, that isn't going to be the best display of the stiction involved in the control loop in its normal operation. That's all.
No, 100% agree with you. This is going to tell you that there is stiction. It's not going to tell you how much there is in it. The previous one is going to be a much accurate decision on it. And actually that feeds nicely into my next slide, which is, so what are you going to do about it? You know, and if we look at this slide here, there's a couple of different output profiles here based on different aggressivenesses of the tuning, and you can adjust your tunings to compensate for your stiction, but you cannot fix stiction using a tuning change. You can reduce it, you can soften its effect, but you will not remove it, because it's a mechanical problem. It's not a virtual problem, it's a physical problem. The couple of rules of thumb on stiction: if you have 1% stiction, increase your integral, double your integral time. So now again, it's not double the number, it's subject to whether you're above or below the line with your integral value, but what it is to do is slow down your integral effort by double if it's 1%. If it's 2%, you slow it down by another double, 3%, etc., etc. So what's anybody in the group here, in the audience here, that thinks, well, if I'm going to increase my integral time by double, it's going to get radically different, and you're going to lose the ability to accurately control. But what you are going to do is you're just going to change the frequency of oscillation into a longer cycle. The oscillation is still going to be there. The lack of control is still going to be there. You're just going to spread it out over a longer period of time. Should you be concerned about stiction? Absolutely. 1% stiction is 1% loss of control. So on your process variable range, you've lost the ability to accurately maintain 1% of. So a 0 to 100% instrument, you've lost 1% of temperature control. If you need to control your process at a better resolution than that, 1% is a problem. 2%, 4%, they're obviously they're getting worse. 1% is concern. 2% should be planned action, and 4% should be you need to do something now, would be the way I would suggest it. You can set your own limits on that based on how much, how close do we get to an alarm with lack of 1% of instrument range is the effect on it, and that should drive your decisions to go, are we going to do something about it now? Are we going to do something about it next week? Or are we going to do something about it on our next shutdown? You can track that through your predictive analytics. We have tools that will help you show that information, and you can then make decisions on when you're going to interact with that valve. You're to plan the shutdown, schedule it for between batches, between cycles, etc.
Damien, if I can interject, our boss, Dr. Bob Rice, our Vice President of Engineering, he always refers to a control loop and the system it's in and the design level of operation. What can this control loop or system tolerate as far as variation?
Yeah,
that's the question for anybody who works in the plant.
You have to ask that. In that example there, is this amount of oscillation acceptable, or is this amount of oscillation acceptable at your target point? You know, and that's the rules that you need to work to. Absolutely, Brad. Next one is deadband. Now, Stiction, deadband, and hysteresis is next. They have similar characteristics, but they're actually caused by different actions, I suppose, or different mechanical constraints, issues, or scenarios. Deadband is when we ask the valve to move and it works fine, but then when we move it in the opposite direction, it has to overcome a degree of slop in the valve, looseness in the connections, which can be caused by a lower quality valve. It can be caused by wear and tear on the connectors, the buckles, the linkage arms. It's not necessarily a friction issue, because the friction issue will remain there all the time. But deadband typically is from a degree of valve lash, is what it used to be called. This looseness in the components. It's less and less prevalent in valve design now. A lot of that has been designed out of it as we've moved away from classically pneumatic and linkage controllers to more direct drive controllers, direct drive valves, etc. But it still exists. It's still in there in the process. The detection of it is that when you reverse direction and you get no motion. Typically, stiction will work in both directions, because that stiction is overcoming that static friction, whereas deadband tends to, you can work up the stroke, up the opening of the valve very effectively, but when you change direction, you have to take up all of that slack in the mechanicals of the process before it will re-engage or affect the change in the other direction. You know, this continuous cycling produces oscillations. It builds up that wear and tear in the mechanical components. If your valves have a lot of mechanical components, watch out for deadband. What causes it to grow? Oscillations. What causes the oscillations to grow? Aggressive control of your process, over-aggressive control of your process. I know there'll be people in the group and the audience that say, but we need aggressive control because of X, Y, and Z. Well, understand those X, Y, and Z's and then make decisions on how you can control better at those processes. Yes, there are certainly systems that need fast, aggressive, active control, but not every one of your systems. And it's a habit that I've seen far too many times. Just because you can doesn't mean you should. You know, aggressive control is never better control. Aggressive control is sometimes acceptable based on a certain set of scenarios that you have set during your why am I here question. Why am I standing in front of this loop or this valve that's not performing like we did. We've all, well, perhaps I'm speaking for you, but I've regularly been in front of a control loop and says your PID is not functioning. In fact, the PID is probably the thing that's most perfectly functioning. It's the material and the equipment it's using which has started to struggle. And whether we like it as not, as process engineers, automation engineers, we have a strong hand in ensuring that performance by ensuring we're operating that equipment as efficiently and as conservatively as possible. Just enough, like the just-in-time philosophy of maintenance, we should develop or adapt a just enough control philosophy, that we're doing just enough to maintain control. Moving on from deadband, we're going to look at hysteresis. Now, hysteresis is more like a process-related problem, but can be mechanical too, in that the action of the process exhibiting in our system will exhibit a different profile in the upstroke than in the downstroke. Some of this, good examples of this would be when you're running a flow system or a pressure system and going up the load or pressure curve or flow curve, you will have greater effect as you move up through the stroke. But on the downstroke, when we're trying to close out that system, back pressure, back flow, reduction in flow can change the effect of that based on where you're operating at higher flow rates or lower flow rates. It's it again can exhibit itself as positions based on where the valve is taken up, but typically, in my experience, I've seen it with systems where we've had high flow rates and low flow rates, or high pressures and low pressures, and the effect it has across the butterfly valves, particularly, you know, the lower quality, lower important systems will exhibit some of this more so. You know, for the same controller output, for the same percentage on the output, we have different valve positions and ultimately flows or pressures. So it's going to have those different conditions based on the same valve position is the effect of it. Now, if we just talk back to or look back at the two slides that I just talked about, it can exhibit very similar characteristics to Stiction and to deadband. So it's understanding your mechanical processes before you start to look at your processes, I suppose. A very good tip and trick that I would recommend is stand beside your piece of equipment and understand when the control system changes, you know, and I've done it across a radio on a number of occasions. Stand beside the valve with a finger on the stem of the valve and ask for a 1% change. Does the stem actually change? Does the flow rate actually change? So that you're making those connections between the virtual control system request and the physical control valve response. It can be very useful to understand what's causing this, to see, and then in the other direction, are we getting the movement but we're not getting the flow change? Are we not getting the movement and we're not getting the flow change? Are we getting if we're not getting the movement at all until it takes a couple of steps to do it? You know, all of those will give you that information. Not always possible. Restricted environments, locations of instruments, insulation, all of those things can prevent that in-person understanding of what your mechanical problems are. But it's something that you can work to.
Damien, if I could interject
yes,
here, when we're dealing with loops and fail-safe modes, a lot of times there will be a spring return actuator to move a valve either fully open or fully closed. If the pneumatic actuator for the valve has not been designed properly, sometimes the spring action on the return is can be greater than the force that you can apply with the actuator, so you end up with trouble there, and may end up with this pattern you're seeing.
Yeah, absolutely. The other of that would be those spring actuators have a certain life and cycle on them. If they've spent their life compressed, you know, because of valve sizing potentially, it's lived in the fully compression on the spring. The spring performance is going to decay over time. It's one of those long-term scenarios. If this process has lived because it's in a fully open or fully closed, or mostly open or mostly closed because of valve sizing, that's the kind of scenarios that you could develop over time, even if the design and balance was correct. But Brad, well taken on that point. The next one here is, how do we tune these? How do we tune for hysteresis? How do we tune for deadband? I've indicated that basically, if you have one of these conditions, tuning is deadband and stiction is integral, but hysteresis is conservative. Is the rule I would segregate them. If you've defined that it's a stiction problem, slow down your integral. If you've defined it's a deadband problem, slow down your integral. If you defined it's a hysteresis problem, be more conservative. You can do that with both the proportional and the integral. You can decide to step back on that. Now, you're changing your tuning parameters. You're not changing them for a good reason. You're changing them because you cannot get at the mechanicals. You cannot change the hysteresis on this until we upgrade the process next year. You cannot get at the packing of this valve because we don't have a shutdown for another 3 months. They should be the only reasons that you retune a system, because of mechanical deficiencies. And unfortunately, it happens regularly that people go, can you retune that loop? It's not performing. You're retuning for mechanical issues. So you're not root cause analysis, and you're not getting to that root cause and fixing the problem. Granted, the problem may be hard to fix, and it may take a shutdown to do it, but it's something that you need to build into your process to go, we can tune this, but we're putting a maintenance action in at next shutdown. We're going to address the mechanical limitations, weaknesses on that process. At this point, I'm going to back to Michelle for questions, perhaps.
Thanks, Damian. So on your toolbar, excuse me, there is a bar called questions. On the right-hand side, if you click on the little box that says undock, you can undock your pane and type in your questions. We have two excellent engineers here with a lot of experience. Please come with your questions. If you want to go to the next slide, Damian.
Sure.
Also, too, if you like to take out your cell phone and snap a picture of the QR code, that will take you to everything on our website. We have industry-specific white papers, case studies. There's also a chance to sign up for future webinars, trainings, all that good information. And while you're typing the questions, we got one here. Why does the slide say no positioner is no prediction? I think we're going back to that chart in the beginning, Damian.
Yeah, let's go back to it, and we'll cover it. I have to find my slides. 1 sec. No, I'm the wrong way.
That's okay.
I know the slide we want to get to. Nearly there.
Slide 6.
Get
yes.
close. Get close.
I should have typed it in. I suppose that I'll remember that the next time. Slide 6. There we go.
There we go.
So no positioner needs no prediction. Brad, I'll let you go first.
Well, typically, you know, positioners do help you try to get to the desired control output. I mean, it's not fail-safe. Some plants or that I've been exposed to, you know, don't haven't used positioners that much. Um, you know, it's more of a personal preference, but I think nowadays most plants are leaning in that direction. Damien, what's your
Yeah,
take?
again, it's, a positioner is going to give you that feedback. And in reality, a lot of modern valves have internal positioners so that they will correct internally rather than send the signal all the way back to on an analog card. But now, when I say if there's going to be a positioner, it's more likely going to be internal to the valve. So we have no feedback to that. Now, again, I would expect if we poll the audience here that the number of positioners that you would have on your processes are probably quite low. I would expect less than 5% of your valves would have positioners. They're only really put on critical valves, and to my comment about, the amount of stiction, if you are concerned about 1% poor performance, the likelihood as a positioner is going to be a real benefit there, because it's going to ensure that what the control system asks the valve to go to, it's mechanically and physically going to go to, regardless of weaknesses in the process or weaknesses in the signals, I suppose. So that's so the prediction is, we can predict, we have some software tools that will give you some of that prediction, and it's quite accurate. So, equipment that doesn't have positioners and ultimately no prediction, we can help you on that, is what I would say. Hopefully that answers your question.
Okay, we have another question. I'm also going to pull up our last poll. So while the gentlemen are answering the question, you guys can take your mouse and click the last poll. I'm going to pull that up first. You should see it any minute. Please have someone from CS Control Station provide more information about software proven to accurately model and tune dynamic processes, which we talked about today. We also have PID tuning workshops that are excellent. We also offer solutions of partnering with you to meet your plant's reliability and sustainability goals, software to identify control loop performance issues, or evaluation opportunities to identify issues at your facility. So pick all that you're interested in and we can get you that information. All right, the next question is, when you say reduce your integral, if my integral is 1 minute, am I making the number smaller or bigger?
So what I would say is reduce your integral effort. Be less aggressive with your integral. Now, integral can be above the line or below the line. If it's above the line in the calculation, it's integral times the error, which is going to make a bigger number, which is going to give a more effort to your integral effort. If it's below the line, it's going to you want to, if it's above the line, apologies, you want to make the number smaller. If it's below the line, if it's 1 over integral, you need to make the number bigger, so it makes the effort smaller, is the difference. There's effectively 2 forms of the integral use, above and below the line, I suppose. So the real result is make your effort smaller. How you're above or below the line will answer that. Hopefully that covers that. I can, again, the question, if you need further clarification on that, as with if you want a control station to contact us, if you have questions on this, feel free to reach out to us, and we can respond independently to those questions.
Damien, one thing I always stress to the people that I'm working with is to understand your control system, whatever DCS vendor or PLC vendor you're working with, because the nomenclature that is used is not standard.
Oh, absolutely, yeah. Again, sorry, go ahead.
You can't, whatever vendor A says as far as integral what Damien was driving at versus vendor B. Vendor B might be repeat time in minutes, and vendor A might be repeats per minute. So you need to stop, and especially if your plant has more than one DCS, to understand what the way each vendor phrases for all these terms. I know it's
Yeah,
hard. I know there's a movement afoot in the ISA to try to straighten this out, but it hasn't, reached industry-wide adoption yet. So that is that's my takeaway there, is to understand the nuances of each control system you're working with.
yeah. What I would say is we have 140 different algorithm forms in our library for the various different vendor types. There is a high degree of similarity between them, but they all have nuances. So understanding those is very useful, and as Pratt says, very important. If you need help with that, feel free to reach out. We can have a quick Teams call on the forms you have, and we can explain the flavor and what the best approach is for it.
Okay, Damien, do you want to pull up the contact slide
Yep.
so people can see that? And we'll continue with the questions here because we do have a few more to get to. One more slide, please.
Sorry. Yeah.
One more.
And one more after that. Yeah.
There we go. Okay. So we have Brian and Alessia in North America. We also have a new member to our team. Yay. We have Keith Brooks that be handling the east side of the North America. We have Damien's information right here, as well as his colleague Kathleen, if you would like to contact them. I'm going to go on to the next question. How can an automatic algorithm detect stiction if we have around 1,000 PID loops in one plant?
So what we have a tool called Plant ESP, which is going to look at the performance of your PIDs over time. It can look for stiction events in your process data. It's going to look at the relationship between what we ask the valve to do and what the process and how the process variable responds. So it doesn't need that feedback. If we had physical analog input feedback from the valve to what the actual position was, you could accurately calculate it. But again, the reality is there's one analog related to a control valve, and it's an output to it. Very rarely is the feedback coming back from it. So you can, over 1,000 loops, obviously you can't go around and do a manual 1.1% step on each one of those loops, but we have analytic tools that can look at that. Can you build those yourself? I would say good luck to you. There's a lot of efforts that go into the accuracy of that. Our metrics will give you those performances, and more importantly, you need to correlate that stiction or poor performance to the overall valve performance. Is it oscillating? Oscillation and stiction are directly connected. Oscillation and tuning are directly connected. So if you have a loop that has started to oscillate and your process hasn't changed, you can correlate that you've got a mechanical problem. If you use our tools, we'll show you exactly where the problems are, is what I would say to you. But if you look at your process data from today, a month ago, and a year ago, and if your process is very constant and you're starting to change, the likelihood is it's mechanical. To define it then is a further step from there. But oscillation equals poor mechanical performance. Our process has changed, and thus your tuning performance has changed. Hopefully that answers your question, but it's going to give you something to point at. Come talk to us about Plant ESP, and we'll show you how we can monitor, detect, and report stiction within 4 hours of it happening, I suppose, is what I would say.
Okay, we have another question. I know we're at time. We will hang out and answer your questions as long as you ask them. Brad, Damien, do you have a commitment?
No, keep going. I'm okay to stay with
Okay,
it.
fantastic. In
Good
order to
here.
accurately determine, pardon? Brad?
Said good here.
Okay, thank you. In order to accurately determine issues based on trending data, what kind of sampling periods do you recommend for the PV, OP? Asking because we wouldn't want data sampling rate to mask issues.
That's a good question. I have someone who knows their data analytics. So what I would say to that is, technically, you should sample your process data 10 times quicker than your process time constant. That's the science of it. So what does that mean? If it takes you 3 minutes, let's keep the maths easy. If it takes 30 seconds for the process to change, you should be sampling at a frequency of 10 times quicker than that, which is 3 seconds. Now, if your process takes 3 minutes or 45 minutes to change, then 3 second or 1 second data is going to be more than fast enough. The reality here is that typically sampling rates in your historians are all set at a standard, or perhaps you have two standards, a fast collector and a slow collector. If you think about your loops, flows and small pressure systems are fast. Small temperature heat exchanger, single pass heat exchangers tend to be quite fast. Large vessel jacketed reactors tend to be slower. So you can do rules of thumb on your historians to adjust your sample rates. But the reality is you're not going to have a different collection rate for every instrument out there of the 1,000 loops that are on your plant. So typically 1 second data is what most modern historians are collecting at. There was a time in the past, 15, 20 years ago, where storage was expensive. That day has gone away. So 1 second sample rating with archiving is made it much more usable. So don't get too caught up in that consideration, but try and get as fast a sample rate as you can. A lot of the programming softwares have built-in trend functions, which tend to trend at the OPC collection rate, which can be 10 to 100 milliseconds. I think most of our audience is in process, which is, although is considered relatively high speed, the people here from the paper industry perhaps would need to move quicker to millisecond sample rates. But in the mining, in the food and beverage, in that typical process manufacturing, and the non-high speed side of paper, 1 second data is more than fast enough. Next question. Or Brad,
Yeah,
have you any? Brad, are you okay with that?
Yeah, I mean, Control Station has general guidelines that we give our customers as far as sampling that Damien has touched on them. But the overriding factor is, what is the design level of operation of this loop process system, and use that accordingly, because like I said before, no loop runs in a vacuum. So you have to kind of step back sometimes and look at the big picture. That's all.
Okay, we have one final question. Damien, I think this one's for you. What would be the most important advantage of the Loop Pro software from other tuning tools on the market, and is it sold separately?
So yes, it's sold separately. That's the easy one. It's Loop Pro is our tuning software. It resides on your programming workstation. It will work in the same way in which you would use your programming software. It will connect to a loop. It will model and understand that loop, and it will give you the tuning parameters to use. So it's a plug, connect, and then disconnect. It is sold separately to the ESP tool, which is the monitoring tool. The ESP tool is the continuous monitoring function on it. So the Loop Pro is your commissioning, change in process, understand your process model, and develop tuning parameters for those loops. The ESP is the ongoing reliability, maintenance, performance adherence tool to ensure that your process is still doing what you designed it to do.
Damien, I like to think of plant ESP as the process control engineer that stands in the corner that never takes a vacation. It's monitoring your loops 24/7, 365, all the time, and it tells you when things are heading in the wrong direction before most humans would ever even see it.
Yeah, I again back to my why am I here question. Plant ESP is going to tell you those things before you show up. You know, before you get called by operations to say, we have a problem over the weekend, this happened. You know, Plant ESP is going to show you those things when they start to happen, not when you hit your alarm limits. Remember, your control system is not a performance management tool. Your control system is making product. It's not monitoring your performance except when you hit alarms. It will prevent you causing problems, but it won't proactively tell you when your process is starting to change.
Okay, I think we've covered everything. Damien, Brad, thanks. Great information. Thanks again for sharing your personal experiences in process control. Again, I want to reiterate our final public webinar is December 5th, and it's on oscillating. We're going to be doing a case study. It will be Brad again, Brad Anderson, as well as Dr. Bob Rice. So thank you. Appreciate your time today. Brad, Damien, thank you.
Thanks very much for staying around with us, listening, and the good questions. Enjoyed those.
Thank you, everyone.